Hi guys, in this video we'll be discussing the problem of the day for Geeks for Geeks, and the problem's name is maximum value. The statement for the problem is that given a binary tree, find the largest value in each level. So let's get started. So firstly, what is a binary tree? So a binary tree is basically a tree with at most two outgoing edges. So this is a node, right? So for this node I can have either 0, 1 or 2 edges. So these are binary trees, right? So this has two edges, this also has two edges. Let's say this has a single edge, this has no edge, no outgoing edge I meant. So these are all valid binary trees. Similarly, we have ternary trees and so on and so forth, but the question states binary trees. Also, what's the difference between a graph and a tree? So a graph can or cannot, may or may not have cycles in it. So this, for example, is a graph but not a tree because it has a cycle in it. On the other hand, this is both a graph and a tree. So every tree is also graph, but not every graph is a tree, because if a graph contains a cycle, it won't be considered a tree. With that, let's move ahead. So the question asks that for a given tree, so let's just draw a tree over here. So let's say this is a tree, and let's put some random values over here. Let's say 3, 4, 10, 12, 26. We have to calculate the maximum value at every level. So what are levels? So levels are, if we start at the root node and we start by going one edge deep, or we start traversing at a single depth. So this would be level 0. This is the root node. Root node is basically the node at which you start, right? This would be the level 1. This would be the level 2. So since they had asked us the maximum value at each level, so the maximum value at this level would be 1. The maximum level at this would the maximum value at this level would be maximum of 4 and 3. So that would give us 4. The maximum at this level would be max of 26, 10 and 12. That would give us 26. So the array we would have returned, if this was the sample case given to us, would be 1, 4, 26 in that order. Now this was how we calculated just now, but what would be the algorithm for this? So as you saw that we need to be at a certain level simultaneously. For example, in iteration 0 I want to be at level 0, and at iteration 1 I want to be at level 1, at iteration 2 I want to be at level 2. So the algorithm I can use over here is called BFS, or breadth first search. In BFS we traverse a particular tree or a particular graph level by level. So I'll be at the iteration 0 I'll be at the root node, and then I'll be traversing all of its children, all of its immediate children at my iteration 1. Iteration 1, this was iteration 0. In the iteration 2 I would be going to all of the immediate children that belongs to these nodes which were at level 1. So I will be going to all of these children, and so on and so forth. And since this satisfies the thing we need, hence this would be the best algorithm to deploy. Now to formalize, I'll be writing the pseudocode of this algorithm. So before that, it's required that you understand a concept known as queue. I'm pretty sure that most of you know this already, but for those who you don't, I'll be explaining it in brief. So queue is a data structure. So let's say we have an array, and the queue is a FIFO data structure. So FIFO means first in, first out. As the name says, let's say there are 10 people waiting in a queue, right? So this array now became actually 10 people. So this is almost the similar concept, right? So there are 10 people waiting at a movie counter. So the person who came first would be first in the line. The person who came second would be second in the line. The person who came third would be third in the line. This is the counter. So the counter would serve the first person first, right? So firstly it will be processed, then this one, then this one, so on and so forth. So I hope this concept is clear, and this is a very easy concept. So we'll be using a queue, and a queue is generally used for BFS, right? So the pseudocode would be something like that. The question already gives us the root, right? So we can create a queue and push the root in it. Then we can say that while this queue is not empty, while not queue empty, let's just call it queue for ease, queue dot empty. I'll keep traversing it. Now while I'm traversing it, the size of the queue would give me the number of elements at that particular level. So initially I would be having a single element at iteration 0, and its size is also 1, right? So I'll say size is equal to queue size. Once I have that particular size, I'll try to go through all the elements of that particular queue. So I can have a for loop or a while loop, and at a certain iteration of this particular loop, I'll firstly be fetching the node value of, so it's the node is queue front. So whatever value is at the front of the queue, I'll be removing that value from the queue itself, and then I'll be checking if it has a left child. So a left child for a node means that since we were talking of binary trees, it can have at max 2 childs. So the child that is attached to the left is called the left child. The child that is attached to the right is called the right child. If it has a left child, then we'll push it onto the queue. If it has a right child, we'll push that onto the queue. Queue dot left and queue. Okay, so queue dot push node dot left. Sorry for messing this up, but you got the idea, I guess. Cool. So after this is done, what I can do is that over here I can also have a variable that can be used to store the maximum value. So let's initialize it with 0, and over here I can say that mx, the variable which we have defined over here, would be maximum of the value it's having or the value at the node. With that we can close this particular loop. Also, once we are out of this loop, so this means that the entire level has been traversed. And all the children of this particular level have now been added onto the queue. So since the level has been traversed, our mx actually contains the maximum value that was present at that particular level. So we can also have a vector int, or let's say array result. So we'll push this particular value onto the array. So mx will be pushed onto the array, and then we'll return the array. Now if you didn't understand this, so let's try it with us with an example. So let's say this is the particular example we had, or let me just draw a random tree over here. So 1 3 4 7 8 9. So initially the queue would be pushed with this particular node. So queue pushed 1, and then we'll start the queue, and we'll say till the time it's not empty. Okay, so, and then the size at the first iteration would be 1, so it's queue dot size. This is set as 1, right? And then we'll start the while loop for size. In each iteration, what I'll say is that I know that the node I'm pointing to is the one that had the value 1. So it's not int, but it's a node. So it's the one with the value 1, right? Okay. And then we can say that if it has a left child, yes, it does have a left child. It has a left child as 3. Then I'll push 3 onto the node, onto the queue. So I'll push 3. So over here, if you realize, the queue was having a single element, that was 1, right? Now the queue has two elements, that is 1 and 3. I'll say if it has a right element, then you also need to push it. So does 1 has a right element? Yes, it does have a right element, that is 4. So we'll be pushing it over here. After that, what we'll do is that we will remove 1 from here itself. So then we'll cancel out 1. So we'll pop 1 from here, and then we'll continue. So since our size was 1, so now this while loop would become invalid, and we'll get out of this queue. Also, we had initialized mx is equal to max node value comma mx, and we'll push 1, that is the present value of this mx. So we'll push mx onto the array, and the array would now become 1. Now we'll again come over here, we'll see if the queue is not empty. Yes, it's not empty, it's already having 2 elements. What's the size of the queue? It's 2. Again this process would start. We'll see what's the node. So what's the value at the start of the queue? So it's 3, so we'll point it at 3. Does 3 have a left child? Yes, it does have a left child, that is 7. So we'll write 7. Okay, so we'll write 7 over here. So this is the queue. Okay, this is the array. Cool. Does it have a right child? Yes, it does have a right child as well. It has a right child as 8. So we'll write 8 over here, and then we'll pop this 3 from here, and also set mx to be the maximum value of mx or node. So mx would initially be set to 0, so mx now would become 3. Now the while loop would continue because it has a size of 2, and now it would continue because now it would become while 1 minus minus. So it's still not invalidated. So now I'll check what's the starting of the node. So it's a 4. So I'll give a 4 over here. Then it will ask, does it have a left child? Yeah, 4 has a left child whose value is 9. So it will add it onto the queue. Does it have a right child? No, it doesn't have a right child itself. So nothing would be added onto the queue now. Then we'll pop out 4 itself, and we'll update mx to be the maximum of the node data or the maximum value. So it would be the max of 3, 4, that is 4. Now this loop would become invalidated as as in the earlier loop we had 1 minus minus. Now it becomes while 0, which is an invalid condition. It gets out of that particular loop. Also, we push the maximum value or the mx onto the array. So the mx over here was 4, and the queue size now is 3. So now it will again check while not empty. Yes, it's not empty. What's the size now of the queue? It's 3. Okay, so we'll start with this while loop. What's the element at the start of the head? So it's 7. Does it have a left child? No, it doesn't have a left child. Does it have a right child? It doesn't also have a right child. Cool, then pop it up. So we popped it. What's the mx would now be initially set to 0 in this loop as well. So we'll make mx as 7. Again this loop would continue, and this loop would say what's the first element of the queue? It's 8. Does it have a left child? It doesn't. Does it have a right child? It doesn't. So now pop it up, and change the mx to be maximum of the node data or the initial value it's having. So initial value it was having was 7, and now it will change to 8 because 8 is greater than 7. Again the same process will follow for 9 as well. So it will check the first element. So it would be 9 now. If it has a left or a right child, it has neither a left nor a right child. So these statements won't execute. Now we'll pop it up and store mx to be the max of the value it's currently having, which is 8 or 9. Since 9 is greater than 8, its value would be updated to 9. And now this while loop is invalidated. So this while loop is invalidated now. We'll get out of here, and we'll push the particular value onto the array. So 9 is now pushed. So this is the resultant array. We are having 149. So 149 is the resultant array we are having. For this particular tree, we can see that the first level has a maximum element 1, the second level has a maximum element 4, the third level has a maximum element 9. Hence the answer and approach is correct. Now let's get to the solution or the code. So over here I've implemented the same thing in C++. You can implement the same in Python, Java, or whatever language you want. So we are started the question with a queue of type node, so that I'm able to store the nodes in it. Then I'm pushing the root node. So the node provided initially is the root node. Once done with that, I'm traversing it till the time it's not empty, or I can say it's till the time it's not empty. I'm keeping the size as the size of the queue. Mx has been initialized to 0 as discussed, and I'll be using this loop size minus size times, right? So size basically is the number of nodes at that level. With that, I'll firstly pop out the node, then I'll say change mx to max of mx, or the node's data. If it has a left child, push it. If it has a right child, push it. And once this loop is invalidated, that means all the elements at that particular array have been traversed. Then we'll push the maximum on top onto the resultant array or vector, whatever you are using, and then we'll simply return it. Let's try running this particular code. As you can see, this is successful. The total time taken by this code is 0.11 second, and it's able to pass all the 150 test cases. I hope I've been able to enlist all the concepts that have been used over here. Although the question is pretty simple, but someone who doesn't have a knowledge about binary trees or graphs as a whole might face some difficulties solving this. So in case you have faced some difficulty or you want some more clarification, please do let me know. Thanks a lot, guys.